All right, let's do an example where you actually need some calculus and you couldn't do it with some basic geometry. Example 2 says, evaluate the area enclosed by one petal of the rose curve, r equals 2 times cosine 3 theta. So to graph this, and I do recommend you graph them always so that you can figure out your bounds. So to graph this one, I would recommend just plugging in 0 for starters for theta, and you will get 2. Then really, if you think about it, we're expecting 3 petals. They're evenly spaced, so you would have 1 petal every 2 pi divided by 3 radians. So you'd have a petal at 2 pi over 3, and then a petal at 4 pi over 3. Oops, that was really good. That was looking good. All right, now let's talk about, for part A, it says evaluate the enclosed area, but of just one of the petals. So, to do so, one way would be to figure out, well, what angle causes this petal to begin and what angle causes it to end. And this petal begins and ends with r values of 0. So solving for that, you could just go back up to the original equation and replace r with 0 and just solve an algebraic equation. So looking for when the function of theta here equals 0, divide by 2, just to isolate the trig function. And then this is what I'd call unit circle ready. So we're thinking about when is the cosine equal to 0. So that means our angle, which is called 3 theta, just on this first rotation, or actually just a little positive, a little negative, could be plus or minus pi over 2. And then dividing both sides by 3, you get plus or minus pi over 6. So on your picture, if you were thinking that it kind of made sense, that it looked like it could have started and ended at plus or minus pi over 6, then you were right. But now you have an algebraic way to make sure. All right, so there are a couple ways that you could set this up. Finding the area of one petal based on what we've done here, and using the formula that we talked about, we'd have area equals 1/2 times the integral from negative pi over 6 to positive pi over 6 of r, which is 2, times cosine of 3 theta squared d theta. Now a comment here, you can do this problem this way, it will work out just fine, but for anybody who likes having one bound of 0, you could take into account that you could find the area of half of this petal and then just double it. If you did that, you'd end up with area equals 2 times 1/2 times the integral from 0 to pi over 6 of 4, we're just squaring that out, times cosine squared 3 theta d theta. Now either setup will give you the same answer. We're just trying to show you how you could take advantage of some symmetry and get one of your bounds to be 0, which in the end ends up being kind of a time saver. So going from here, 2 times 1/2 is just 1, and then we could factor the 4 out. From there, anytime you have just sine or cosine as your integrand and it's squared, or to any even power for that matter, you're going to need to use the power reducing identity, which here would be 1 plus cosine of double the angle you used to have, so double 3 theta would be 6 theta, all over 2. There we go. Now the 4 and the 1/2 could merge together, making a coefficient of 2 out front. And we'd have 1 plus cosine 6 theta left inside. All right, now time for the antiderivative. We'd have 2 times theta plus 1/6 sine 6 theta from 0 to pi over 6. There we go. All right, plugging in your upper bound. Now a note for the next part, so Bryce doesn't have to write it all out. 6 times pi over 6 is pi, sine of pi is 0, so you'd end up with just plus 0 when you plug in pi over 6 to that second piece. Then plugging in 0 into this entire rule for your lower bound would give you a result of 0 for the whole shebang.
Whoa, I don't know what that was.
So you're left with just 2 times pi over 6. And that gives us an area for that single petal of pi over 3 square units. All right, and that's it for part A. Moving on to part B, it says evaluate the area of the region lying inside all 3 petals of the curve. So the idea is if you found the area of one of the petals, you just need to multiply it by the number of petals. There we go. So your answer would be pi square units.